version of the Turing test, a computer plays the part of either the man or the woman in the imitation game, and the interrogator simply has to work out which respondent is human and which respondent is a machine. The question is, would the interrogator decide as wrongly in this new standard interpretation of the Turing test as they did in the imitation game? If they did, we might say that the machine that the interrogator is interacting with has in some sense passed the Turing test. Now, one of the subtleties of the Turing test is that the interrogator is allowed to ask questions which range over the entire human condition. They can say, compose me a sonnet on lost love, or write me a poem on the wetness of rain, or tell me who won the 1966 FA Cup final, or whatever. Another subtlety is that the interrogator knows a priori that one of the respondents is a machine. There's no doubt about that. One is a machine and one is a human. The third subtlety, as I said before, is that the respondents are allowed to lie. The only thing that we expect of respondents in the Turing test is that they enter into the spirit of the game. If the respondent every time just said banana, banana, banana to every question, then that wouldn't make for a very interesting game. So we ask that people enter into the spirit of the game and respond to questions sensibly, albeit that they can lie if they wish. Now, in Turing's 1950 paper, he confidently predicted that by the year 2000 there would be computers with a gigabyte of storage. This is quite astonishing if you think about the time that Turing wrote that paper. The very few computers in existence in the world had storage capacities in the regions of perhaps a few thousand bits of information. And yet Turing accurately predicted in the year 2000 there'd be machines with a gigabyte of storage. He was right about that. Turing also predicted that there would be computers by the year 2000 that would be able to perform the Turing test such that the average interrogator, this is an important qualification here, average interrogator, in a Turing test would not have more than a 70% chance of making a right identification after 5 minutes of questioning, i.e. they would 30% of the time be wrong. Now, as an aside, this prediction is a little ambiguous. Did Turing mean a 5-minute test, or did he mean 5 minutes of questioning per respondents? If it's the latter, then of course the test would take 10 minutes. If the former, it would take 5. But in either case, to date, Turing has been proved wrong. That has not happened. Yes?
Mark, I just want to ask you about Eliza. You know the Eliza the software?
Yes,
How
I do.
Eliza was on this test?
Well, there's a very famous anecdote. Eliza was a program written by the scientist Joseph Wiesenbaum, and there's a very famous anecdote which everybody believes to be true, but I can't say I've actually checked this out for certain. The anecdote runs like this: that Eliza is a very simple program, really simple program, that in one of its incarnations behaves as kind of a psychoanalyst. And it is triggered to respond to particular words. So a dialogue with Eliza might write on the screen, hello. And you might type in, hello Eliza. And Eliza might reply, oh, hello Mark, how are you feeling? And I might go, oh, not feeling too good today, Eliza. And Eliza would pick up on the word, not feeling good. And say, oh, why are you not feeling too good? In the same way that a little child can sometimes throw questions back at you. And you say, oh, I'm not feeling too good because my partner left me last night. And then Eliza might say, why did your partner leave you last night? And you can get these pseudo dialogues going on for a long time. And the anecdote goes that a visiting Russian professor to Wiesenbaum's lab in the 60s was totally fooled by this and actually spent 10 or 15 minutes in dialogue being psychoanalysed by this computer program. Now, having played with many Eliza systems over the years, I treat the anecdote with a big pinch of salt because it certainly, I don't think, would fool me very easily. But there is certainly a quite correct an anecdote that over a period of time, Eliza did fool a professor. Now, I can say that this Turing test hasn't been passed, though, because every year, American guy called Hugh Loebner, funds something called the Loebner Prize. And last year it was held in the University of Reading. At the University of Reading last year, I organised a symposium on the Turing test, and in parallel with that symposium on the Turing test, Hugh Loebner organised his annual Loebner Prize event. And that puts Turing's prediction to the test. And Hugh offered a large prize. I can't remember how much now. I think it's around $20,000 to the best program that can interact via text with a human. And I think there's an even larger prize. If I remember rightly, it's around $150,000 for a computer program that can pass the Turing test. Now, in 2008, that didn't happen. We allowed the interrogator 5 minutes to respond to both entities, so they had 2.5 minutes each. And it was too optimistic. The best program that was entered to the Loebner Prize was called LBOT, and that fooled, in quotes, only 25% of these average interrogators. Yeah.
Do the computers have access to the internet,
Yep.
search engines,
Yep.
and
Yep.
online stuff?
Yep. And this is a commercial prize. We have people compete from all over the world every year for the Loebner Prize. Yep.
How many interrogators participated in the...
I didn't run the competition, so I can't give you a definitive answer. All I know is that there are, before the actual event at the University of Reading, there are pre-heats to weed out the poorest computer programs. So only probably the top, for argument's sake, 20 programs were examined on the day, but many others were submitted to the competition and evaluated before the actual Loebner Prize event, and they were weeded out in advance. We have people from all over the world come to test their programs. Yes, sir.
In which matter it's addressed to the questions about likeliness, like what color do you like, or stuff like this?
You can ask any question in the Loebner
Yeah,
Prize.
but how this program is responded?
I couldn't tell you. I don't know. If you go to at the end of the meeting, if you look up LBOT on the internet, you'll be able to you can actually have a dialogue with it and see whether you would have been fooled. And I think this figure is actually, personally, generous to LBOT. But then again, I'm not your average interrogator. I don't think any computer program that I've seen yet would fool me for more than 30 seconds, never mind 5 minutes. But then again, as I said, I'm not an average interrogator, and I'm well schooled at the sorts of questions that these machines typically find difficult. And to be fair to Turing, he didn't say the machine has to fool the expert interrogator. He specifically said, and this is part of Turing's genius, he specifically said it needs to fool the average person. But at the moment, as of 2008, we're still falling short of that 30% figure of incorrect identifications that Turing predicted in 1950. Now, it hasn't been met yet, but it's certainly my opinion that at some point in the next few years, perhaps this year, it's very likely that a time-limited Turing test will be passed in Turing's narrow sense of the word. That's after 2.5 minutes of interrogation of a human and a computer, that the computer will manage to fool 30%, the interrogator 30% of the time. I think that's quite likely to happen. Now, whether that means that at that juncture, as Turing predicted, that general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted, I believe it's extremely doubtful. Now, why do I say that? Well, in 50 years since Turing first published that paper, the very methodology that underlies the Turing test, this notion of this machine dialogue, has been extensively critiqued. And perhaps the most well-known critic of Turing's methodology is Professor John Searle, with his famous Chinese room argument, and that's what I wish to look at next. So just before I move on, though, there's another question about whether some people have doubted you might be able to get a computer to pass the Turing test for 5 minutes in a few years' time. Is it ever conceivable that you would get a computer that would be able to pass an unbounded Turing test? So you'd be able to carry on, you'd be able to chat to it, not just for 5 minutes or 5 hours, but as long as you wanted, and still not realise that it was a computer generating the responses. Well, Searle's Chinese room argument purports to show, and you can make your minds up in a second, how well it succeeds, that even if we had a machine that passed an unbounded Turing test, it would still be a machine that didn't really understand anything about the world at all. So, the Chinese room argument purports to show that even if a computer behaved in a manner indistinguishable from a human in the Turing test, it cannot be said to understand its responses, and hence that really a computer still cannot be said to think. In case anyone's interested, the original reference to Searle's paper is called Minds, Brains and Programs. It's published in the Behavioural and Brain Sciences Journal in 1981. And as I mentioned earlier, for recent discussion, there's a very interesting book by myself and edited by myself and John Preston called Views into the Chinese Room, which looks at modern criticisms of Searle's position. Now, Searle's argument, for whatever you might think about it, rightly or wrongly, it's really had a deep impact in shaping the future of artificial intelligence research and robotics research in the 20 years since it was published. That's a fact. And in that sense, I'm also here in my capacity as well as being Professor of Cognitive Computing at Goldsmiths. I'm chair elect of the UK AISB Society. That's the UK Society for Artificial Intelligence and Simulation of Behaviour. That should be AISB, not ASRB. And this is the world's oldest society for artificial intelligence. And every year we have a convention, and in the 2010 convention we're having a special symposia to examine possible alternatives to the Turing test to establish whether a machine really can be said to be intelligent. And that call is currently out, and we'll be interested to see what suggestions people send us for alternatives to the Turing test. Now, let's first of all, before I talk to you about the Chinese room argument itself, let's describe the context to Searle's work. Searle developed the Chinese room argument not long after two scientists, Shank and Abelson, published information on a program which they had created that could accept as input a story. It could also accept as input questions about that story, and almost astonishingly, the computer program could give appropriate answers to questions about the story. Now, at first sight, that sounds truly amazing. And I should qualify this by saying that the kind of stories that we're talking about were not War and Peace. We're not Wuthering Heights. They were stories of the form. Jack and Jill went up the hill to fetch a pail of water. And the questions were of the form, who went up the hill? And the machine would answer, quick as a flash, Jack and Jill went up the hill. That's the sort of sophistication that we're talking about. But nonetheless, it's still kind of interesting. But the problem was that postgraduates in Shank and Abelson's lab in 1977 were so impressed by this work that they said, verily, for the first time, we have a computer program that genuinely understands. It genuinely understands these stories. And John Searle, when he had a year's sabbatical working in these labs, was so astonished by this claim and the philosophical naivety it showed that he came up with this argument to try and disprove the claim called the Chinese room argument. So, very briefly, Searle uses the distinction between syntax of a computer program and semantics to argue that while computers can follow purely formal rules in their computer program, they cannot be said to know the meaning of the symbols they are manipulating in that computer program, and therefore cannot be credited with an understanding of the programs those symbols comprise. They can simulate intelligent performances, but not duplicate them. Now, around this time, Searle came up with what is now a classic taxonomy of artificial intelligence programs. Weak artificial intelligence says that the principal value of the computer in the study of the mind is that it gives us a very powerful tool. So you might use a computer to investigate certain psychological disturbances. We might use a computer to model neural networks and neural connections in the mind. You might use a computer to model how, say, Parkinson's disease operates. But we don't claim that the computer has Parkinsonism, and we run that model. We don't claim that the computer genuinely has real cognitive states. That type of artificial intelligence is uncontroversial. We call it weak AI. Strong AI is a much more controversial statement, and that says that the appropriately programmed computer really is a mind. It is conscious, it has intentional states, states that are about things in the world. And that's a very strong claim to make. And that seemed to be the claim that Shank and Abelson's postgraduates were making.
Mark, may I
Yes.
ask a question? For example, chess computers playing chess. Where is this on your taxonomy? Is it weak intelligence? Is it strong intelligence?
Well, I would very strongly position a chess computer in the form of weak artificial intelligence, because I would suggest to you that a chess computer doesn't even know it's playing chess. I could take Deep Blue, a very famous chess computer program designed by IBM that beat Garry Kasparov, probably the best chess player the world's ever seen, in a controversial series of matches a few years ago. Matches which, I hasten to add, IBM has never allowed to be replayed. Now the point is, I could take the output from Deep Blue and I can use it to specify the moves of chess pieces on a chessboard, as they did, allegedly. And we can use the Deep Blue program to engage in a very sophisticated and powerful game of chess against Kasparov or another human chess player, for example. But Deep Blue doesn't know it's playing chess. I could take exactly the same outputs from Deep Blue and wire them to a series of lights, so that these lights came on and off in response to where I move chess pieces on the board. Deep Blue is then a kind of an art exhibit. The program is exactly the same. Deep Blue doesn't know it's manipulating lights or manipulating pieces on the chessboard. So again, Searle would say, it hasn't got genuine intentional states, it's clearly a product of weak artificial intelligence. Now, Searle's argument, when I come on to describe it, if it's correct, is very important. Because, first of all, it's important for philosophical reasons. It says, can a computational theory of mind ever explain human understanding? The computational model of mind is, in the last 40 years, has become ubiquitous. If you go to the neurosciences are using computational models to describe what they're doing. You go to psychologists are building all their work on computational models. But if Searle's correct, then fundamentally human thinking is not computational at heart, and all these people are barking up the wrong tree. Secondly, the Chinese room critiques the notion of the Turing test as an adequate test for machine intelligence. And in practical engineering terms, John Searle's argument questions whether computationalism, in the form of this sense plan act cycle, is really the best approach to develop good, strong robotics and good artificial intelligence systems. Now, the importance of Searle's argument has ensured that since its publication, it's been attacked and defended with an almost religious fervour. Having worked in AI labs since 1980, almost 30 years of my life, I find it quite astonishing that the number of postgraduates I've worked with, typically long-haired computer science postgraduates who like whiling their evenings away on games like World of Warcraft, they typically tend to be up to what, if you had a spectrum of people who are very religious on one side, very atheist on another, probably in the main, hardcore atheist people. They protest to have no strong religious beliefs. But the second that Searle challenged the computational underpinning of artificial intelligence, these people got so hot under the collar, they attacked it with an almost quasi-religious fundamentalist stance and got really angry about it at all, as though Searle's argument was questioning their entire ontology. When of course it isn't. Searle is merely questioning whether computationalism, whether the appropriately programmed computer really does understand, or whether we need to look to other models to encapsulate what it is to understand. So, enough background. Let's finish off this section of my presentation with a review of the Chinese room. Now in this paper, John Searle describes a situation John Searle's a monoglot American. He can speak English, American English. He describes a situation where he's locked into a room. And in this room he's presented with a batch of paper on which are written Chinese symbols. Chinese symbols that Searle a priori does not understand. Searle is then presented with a second batch of papers on which are printed Chinese symbols, together with a set of rules for correlating the first and the second batch. An algorithm, you might say. Finally, Searle is given a third batch of Chinese symbols, together with another set of rules, to enable him to correlate the third batch with the first two, and these rules instruct him how to return Chinese symbols out of the room in response to symbols that he was given in the third batch. Now, unknown to Searle, the people outside the room call the first batch of Chinese symbols the script, the second batch the story, and the third batch questions about the story. And if Searle follows the algorithm correctly, the symbols he gives out of the room are answers to questions about that story. The set of rules Searle is obeying is the program. To complicate matters further, people outside the room also give Searle stories in English and questions about the story in English and ask him to reply in English. So you've now got Searle in the room with two different situations. He's given questions in Chinese videograms that he doesn't understand, but he presents, if he follows the program correctly, correct Chinese symbols outside the room in response to the questions in Chinese he was asked. He's also given a story in English, and he gives out of the room, when he's given questions about that story as input, and he gives out of the room correct answers to questions about that story in English. Now I hope you can see that those two situations are fundamentally different. There's an epistemic difference between the two. In the sense of the English situation, imagine that Searle's told a joke. If it's a good joke and Searle's got a sense of humour, he might laugh. He might not just send out a symbol, send out a little note saying ha ha. He will have the phenomenal experience of what it is to find a joke funny. Now if he carries out the Chinese manipulation, he might be given a joke in Chinese, and he might again give out appropriate ideogram that says the Chinese equivalent of ha ha, but Searle will never find that phenomenal sense of finding a joke funny when he's manipulating the computer program. So the two, although from the outside point of view they look the same, in one sense Searle's giving correct responses to stories in Chinese and questions about that story, and he's giving correct responses to a story in English and questions about that story. From the outside point of view they're both the same, but from the first person inside point of view, only in the English sense is Searle getting the jokes about the story. In other words, only in the English sense does Searle understand that story. So Searle points out that he's passed the Turing test, and hence the claim is from strong AI in Turing that he can think and understand Chinese, whereas Searle trenchantly points out that he still does not understand a word of Chinese. So, think about that for a minute. It's been debated. I think there's a lot of power in the Chinese room argument, and personally, what it's worth, I'm pretty convinced by it. But there are, to be fair, to give you a reasonable survey of the ground, so to speak, there are still many people in artificial intelligence and in philosophy who seriously doubt the Chinese room argument. There's a very famous philosopher called Dan Dennett, some of you might have heard of, who absolutely loathes Searle and loathes the Chinese room argument. So if you asked him, you'd get a different perspective on it. But for what it's worth, I think Searle's argument has got some weight. But in any event, the Chinese room argument over the last 30 years has helped shift the focus of robotics away from what we call good old-fashioned AI in the sense, plan, act cycle, with all its importance on and reliance on rich internal representations of an out-there world, towards modern robotics, which is more typically based on this Brooks school of subsumption architectures and a modern European school of philosophy based on the work of Searle, Heidegger and Merleau-Ponty. Further, there are many more recent developments in robotics that, if I had more time, I'd like to talk to you about, where we have emergent or collective intelligence in robots. This school of robotics is called swarm robotics, and some of the work I've been actively involved with in the last 20 years has been looking at architectures and algorithms for controlling swarms of robots, and the ones I'm particularly interested in, for what they're worth, are called stochastic diffusion processes. And just to finish off with, I think, on this section, here's a little video of why swarm robotics is important. Can we turn the volume up?
Until now, it's been the stuff of science fiction. Mini robots joining together, a bit like Lego, to form one big machine, capable of performing tasks too difficult or dangerous for humans. Hundreds of engineers from the UK are working alongside colleagues in Europe to make that vision a reality. Here in this box of tricks is an early prototype for how such technology would work.
The aim of this project, the Symbrian project, is to develop a swarm of robots that can physically self-assemble. What we want to do in the next 5 years is to design the robots so that they can physically join and create a kind of three-dimensional artificial organism.
And this mock-up shows how the swarm robots
Looks like
actually
ants.
operate
Have you ever
together.
seen ants move?
The hope is that given time, they would manage their own hardware and software, even self-heal where damaged. And there are some ambitious aims for how the technology could be used, such as releasing the robots into collapsed buildings. They could work alongside emergency workers to search for survivors, open up communication channels, lift rubble, even apply first aid. But with a mind of their own, should we be worried?
So no risk that the robots may take over?
No, I don't think there's any risk at all of that.
So that's some state-of-the-art research in swarm robotics. There's also some really interesting videos of actually swarms of robots pulling a human, real human, out from a dangerous situation if you look on YouTube. What's interesting and particularly about the swarm robots is that you have robots acting collectively to solve problems that no one robot could solve on its own. Further, if you get into the control architectures of these systems of robots, the work we've been working on stochastic diffusion search is a mode of describing intelligent operation that, again, doesn't really use representations and computations. Instead, it harkens back to that very first slide I put on, that slide of the telephone exchange. And the work on stochastic diffusion search of swarm robotics harkens back to a view of intelligence and the mind as like a big complicated telephone exchange where lots of agents are communicating information together. So it's emergent intelligence through communication, not computation. So with that, I mentioned earlier on, I didn't know whether I'd have time, whether you were expecting a kind of a workshop from me, so I sort of thought what would be interesting to do, and as I mentioned, I thought it might be interesting to run a little imitation game. Now it's nearly 12:30 now, and I don't know whether we'll have time or whether there'll be the desire to do this, but I've finished my presentation, formal part of my presentation. If the organisers would like me to, I'm very happy to run a small imitation game, but if you feel you've got the general gist of it and would rather go for lunch, then I'll totally certainly fund it. So thank you for your attention.
Perhaps there's some questions.
So can I just ask, how long do you think it will take? We'd very much like to do the imitation game, but we have to vacate the room at 1:30 on the dot, really. Do you think?
Let's see, what time is it now?
About 9 minutes.
I think probably it might be more useful perhaps if you've got any questions to ask me, because otherwise we'll have to rush the game and it will defeat the point.
Okay.
So I'm
Do
happy
you have
to...
any questions?
In swarm, any tiny robot can be used as any other, or if one of them failed, all swarm is going down.
One of the things about swarm robotics is that usually the individual robots are homogeneous. They're the same robot architects that you manufacture, many instantiations of a basic core architecture, so they are all technically the same. The project I was involved with for ESA at the planning stage, in the end it didn't get funded unfortunately, was to build some swarm robots for ESA's, this is the European Space Agency, sorry, ESA, for their exploration of the solar system that we can send. So having one big satellite going to do some complicated measurements on the planet, and then the whole mission failing if the satellite fails, what can we do by selling lots and lots and lots of little robots? If one of them fails, it doesn't really matter that much. So swarm robotics is certainly getting treated very seriously by NASA and ESA. Yes?
Sir, I just want to ask you about the interaction between emotions and the learning of a language. You use the example of the Chinese room one was around the Chinese language. That's a different set of symbols, and you said about the whole thing of finding a joke funny. Is there emotion involved in that?
Yeah.
Because,
Sorry.
so the reason why I'm asking is in South Africa we are really struggling with a multi-language environment in teaching, and it's very interesting the stuff that you are saying about the input that if I don't understand the language in those two rooms of Turing, whatever, if I ask you a language, a question in my first language, you will respond quite stupidly because you won't understand what I'm saying. And then the thing of the language and I don't know whether funny is an emotion, but emotion that comes into place. So you only touched on the finding funny, but you didn't say anything more about emotions.
That's a really interesting question. So I'm answering a couple of parts. The basic, just to recapitulate, the take-home point from the Chinese room argument is this. It's that the mere following of rules, the computer program in other words, is not enough to instantiate genuine understanding, because we have John Searle locked in the Chinese room. He was given a story in Chinese, he was given questions about the story in Chinese, he followed the rules of the computer program and gave out appropriate responses to those questions in Chinese about the Chinese story, and yet he never understood the Chinese. And I illustrated that by showing a comparative situation where he's given the story in English, he's given questions about the story, and he replies sensibly in English. And we think about that perhaps with the example of the joke. When he's given a joke in English, he might say ha ha, but he'd actually have the phenomenology, to use the philosophical jargon, the experiential state of finding, the emotion of finding something funny, which he would not have in the Chinese sense. And therefore, epistemically, we would say that these two situations are fundamentally different, although from outside the room, they look really the same, because they're getting correct responses in both cases. Now, the lady's question is, what can we say about emotions and computers and emotions? Well, the Turing test is a very famous test for machine intelligence. John Searle's Chinese room argument in philosophy has reached the status of a minor classic. It's a real touchstone of a critique about whether the Turing test succeeds as a test for machine intelligence. And in my own small way, in that book, Views into the Chinese Room, I give a philosophical argument. I call it Dancing with Pixies. And this argument attacks the very point that the lady said. It purports to show that if I'm correct, if the mere execution of a computer program is enough to give a machine genuine emotive states, genuine phenomenal states, merely in virtue of the execution of the computer program, then consciousness and emotion is everywhere. Philosophically, we say the doctrine of panpsychism is true. Now, in the scientific world that I tend to operate in, most people are led to reject the notion of panpsychism. It isn't a notion that isn't consistent with a standard view of the closed universe and a general scientific materialist description of the world. And therefore, if we reject the panpsychism by the strength of the reductio ad absurdum argument that's Dancing with Pixies, we are then led to reject the notion that a priori no computer program can ever instantiate genuine emotion merely by execution of the computer program. I hope that answers your question. If you want to read more of it, get the book Views into the Chinese Room. There's a whole chapter on this dancing. Or you can go to my website and download one of the papers I've published on this.
Do we have any additional questions? Okay.
Okay.
Mark, thank you very much again.